So back to my part. We have previously talked about the overview of CRAN, then went into the multi-cloud RAN. And previously my colleague talked about the hybrid cloud mobile edge computing framework in a general perspective. And now we take one step further and consider the hybrid networks with rate splitting, as we can see on the right-hand figure. Okay, so in more details, the hybrid networks with rate splitting will be about a general introduction to rate splitting multiple access. Very briefly, then we go into the optimization problem of weighted sum rate maximization within the context of the hybrid cloud mobile edge computing networks, and present the one potential technique for solving this optimization problem, which is referred to as successive convex approximation. And we have touched upon this before, and now we'll find the details of this technique. So there are several related works to the rate splitting multiple access in the context of hybrid cloud mobile edge computing networks. Some of which are general overviews about the rate splitting multiple access, and our recent paper in the IEEE journal on selected areas of communications, which is about the combination of rate splitting and these hybrid cloud mobile edge computing networks. So first of all, we start with this slide that on the left-hand side, we have a figure which shows the evolution over time with the different network generations, starting 1G and going up to future 6G networks. And we see that the available spectrum is rising with the number of, with the generation, and the data traffic is exponentially increasing. And especially towards the right-hand side, interference becomes more and more problematic. Now the thing is that conventional transmission strategies, also which we have discussed previously, utilize a so-called treating interference as noise strategy. So any resulting interference between, for example, two transmissions here, this is a base station and this base station, they transmit to their respective users a message. Each of those transmissions encounters interference. And this becomes, at some point, a limiting factor, especially if the data traffic increases drastically. Now, the idea of rate splitting is to split the messages into a private and common part. So if we refer to the example on the previous slide, we have the two base stations that transmit a message to the users. And what they do now is this message, for example, message 1 will be split into a common part and a private part. So the idea is now still there is interference. However, the common parts that will be transmitted can potentially also be decoded at other users. So as to say that this message gets split into two parts, one part of which can be decoded at other users so that it does not produce interference. And the other part is the private message, which still produces some level of interference, and we can dynamically switch actually the allocation of both common and private parts to manage different situations of interference levels. Now, this rate splitting is a powerful framework for example, non-orthogonal transmission, for multiple access, and for the interference management. And interestingly, this bridges two strategies. One is the treating interference as noise, which we have discussed on the previous slide. So we completely have the interference and treat it as a noise. And there is a NOMA strategy in non-orthogonal multiple access. The idea is to decode the whole interference that arises in the network. And with this rate splitting, we can bridge both strategies as we can determine flexibly the split between the private and the common message. In this tutorial, we consider this so-called rate splitting and common message decoding scheme. Another figure that illustrates the rate splitting multiple access. On the left-hand side, so this is the interference level. On the left-hand side, we have a low interference, as we can see here. And in this case, it would be probably the best to treat interference as noise and proceed as usual. But toward the right-hand side, when the interference is very high, the best strategy would actually be to apply non-orthogonal multiple access scheme to fully decode interference. Now, what rate splitting multiple access does, it partially decodes interference and partially treats the interference as noise adaptively, and thereby we can bridge the two extremes and reach all of those achievement points here. Okay, let's talk about the network architecture. It's similar to the previous presentation, where we have the multi-tier setup with multiple servers. We have cloud tier management instances and the edge tier management instances, and they each have their own set of distinct radio access network resources. So, for example, the UAV has its own computation cycles to allocate, and also its own set of antennas to serve the users with. Same for the central cloud, which has different sets of base stations to serve the network. So with this, again, flexible distribution, dispute optimization of system variables, in this case communication and computation variables, is possible while keeping a reasonable communication overhead between the management instances, so the CC and the UAVs. In this case, again, we have the presence of cloud UAV and intra-cloud interference, as previously also mentioned. And in this case, we mitigate this, mitigate at least the intra-cloud or intra-edge computer interference with the rate splitting multiple access schemes, in this case, rate splitting and common message decoding. In this case, especially the rate splitting scheme is as follows. It happens on a per computing platform basis. That means we do the rate splitting inside, for example, the CC radio access network, and do not allow, for example, a common message of a user in this from the central cloud to be decoded at the edge cloud, because that would significantly increase the communication overhead and would also require a signal level cooperation between the CC and the edge clouds. Now, we focus a bit more on the rate splitting perspective in these hybrid networks and check out the RS-CMD transceiver design. On the right-hand side, you see a figure where we denote some abbreviations. ENC is for encoding, DEC is for decoding, and BF is for beamforming. And this shows an example of the RS-CMD transceiver structure, in this case at the CC in details. So we have the message of a user K, MK, and this is split into the private part MKP and the common part MKC. Now, afterwards, these signals are forwarded to are first encoded into the signals SKC and SKP, and these signals then are forwarded to the base station, which then performs the beamforming and the radio task. And for example, at the receiver 1, we receive a mixture of signals. We receive, for example, in this case, both private and both common messages of both users. And the idea is now that we utilize successive interference cancellation. So we first decode the strongest message that we receive. For example, in this case, it's the common message of user 2. This message is then re-encoded and beamformed, and the channel is added, and then this is removed from the received signal. And what is left here should be the received signal without the common message of user 2. So to say, we have removed part of the interference. Now, network setup. Again, we are in a downlink hybrid cloud mobile edge computing network with 1 CC, E edge computers, B base stations, UAVs, and K users. We have predetermined user association in full CSIT. We again manage the beamforming vectors for the base stations and also for the UAVs, which are denoted as W and V. And they are together formed as a global beamforming vector A. Then we manage the base station to user clustering, the computation allocation, allocated data rates in bits per second. This time it's separated as private and common rates. In this case, we have a data split because we have private and common messages, and we determine by this how much data goes into the private and the common message. And what's also needed is the RSCMD groups. So we need to determine what are the decoding orders, for example, at the users, and which user is decoding whose common message, for example. Now, power consumption metric is similar to what has been previously described. We have power consumption per base station and per edge computer, whereas the base station only cares about the communication or the transmission power, and the edge computer has a joint communication, computation, and operational power constraints. The delay considerations, in this case, they are for the treating interferences noise scheme, which we have previously described. So we have a computation delay, we have a front haul delay, and we have a transmission delay. This is valid for central cloud users, and at the edge, we can ignore actually the front haul delay. Now, for the perspective of rate splitting and common message decoding, some of those delay considerations are changing. And that is the overall user delay in this case is determined by a maximum function. And first of all, we have the private message. Private message consists of a computation delay, which is unchanged, the frontal delay, which is unchanged, and now a transmission delay, where we have an additional factor, which is referred to as epsilon k, determined as the data split factor between the private and common message. So the overall data size of the user dk is further split by this factor epsilon to the private and the common message. Now, this user k is not only decoding its own private message, but also a number of common messages, including its own. And this is reflected upon in the variable mk. Here we have all the messages that will be decoded at this user. And this is itself another maximum function where we have the computation, the front haul, and the transmission delay of all of those common messages. And only the maximum of both its own private and all of the decoded common messages will then tell us what the overall maximum delay of that user is. Now, to the optimization problem. In this case, we want to maximize the weighted sum rate in this rate splitting scenario by managing the beamforming vectors, the data rates, the computation allocation, and the data split factors. This is all subject to the frontal capacity per base station, the maximum computation capacity per central cloud or edge cloud, the achievable private rate per user, and the achievable common rate per user. Furthermore, we have the maximum power consumption at the base stations, which only consists of the transfer power, and at the edge clouds, which consists of the joint computation, communication, and operational power. At last, we have a delay constraint per user. Now, what we see is different from previous problems. We have the frontal constraint, which looks a bit different now. This is the already L0 norm relaxed formulation. Is we have a sum over all users. This is the private rate of user k, and this is the common rate of user k. And this is the association variable q, which tells us whether the private message of user k will be served by base station B. This tells us whether the common message of user k will be served by the base station B. And if this is a yes, then these rates will contribute to the overall front haul capacity frontal link of that base station B. These formulations we have also seen before. This is the constant weight, which will be updated iteratively, and these are the beamforming vectors of private and common messages. Now, previous problem, it is an integrated optimization problem since it is non-convex of mixed integer nature, and we have some fractionalities within this problem. So this is tackled using the L0 normalization. With that, we can tackle the mixed integer nature because we can reformulate indicator functions as weighted L1 norms. We have talked about this previously. Then, to tackle the non-convexity, we utilize successive convex approximation. And to tackle the fractionality, we have already learned about the fractional programming. Now we're going to talk about the successive convex approximation approach in the context of the rate splitting and common message decoding and hybrid cloud mobile edge computing networks. So we start by checking again that we have the frontal constraint where we have the variable Q and R. Both are optimization variables, so we can say that this formulation is bilinear. So what we do next is we do equivalently reformulate this equation as a difference of convex functions. So we start by noticing that the formulation Q times R can be equally written as Q plus R squared minus Q minus R squared. And then we have 1 divided by 4 as a factor in front. So you can do the math and see that this, if you multiply it here and reformulate it, will be the same formulation as this. Just a more complex one, whereas this is a convex function and minus another convex function. This can be done the same for the right-hand side here and will give us the new formulation. Now what to do now is we have the minus convex, which is concave. So we have 2 concave parts in here, which need to be further reformulated, and we linearize them by using the first order Taylor expansion of these concave functions. Now you can find the math in the respective paper, our JSAC paper. But what we find out in the end is that by doing so and doing the first order Taylor expansion, we are able to have a convex constraint where we introduce so-called feasible fixed values. These are usually the optimization variables that were optimal for the previous iteration. And these are usually updated iteratively. And yeah, as a more general view on this successive convex approximation is that we have, for example, a set, constraint set, which is called D, and this is highly non-convex. And the idea of this successive convex approximation now is actually to find a fixed point here. Around that, we approximate a convex set of this constraint, solve the problem for the new convex problem, and then update the variables iteratively. So we shift the convex region up to some of the border points, and in this case, at the end, we will have iterated up to convergence actually. Now the algorithmic solution to the previous problem is we start again by initializing things, do the user-to-server association, for example, proximity-based, or could do the generalized assignment problem. Then we do the beamforming, base station clusters, common and private data rates, and the data split, plus the computation allocation on each device, on each management instance, so the central cloud or the edge cloud separately. And in the end, we can do the information exchange. This overall gives an iterative algorithm, and how exactly we do the decentralized implementation will come at a later stage in the tutorial. Now, first of all, let's check some results. So we have some reference schemes. First of all, we have the fully centralized protocol, and the distributed protocol which we propose. So this is FCP, this is PDP. Then we have a reference scheme which we call central cloud only. This means this is a scheme where we do not employ UAVs and utilize the computation capability of the central cloud only. Then we have the treating interference with noise, which is the baseline scheme we have, my colleague has presented before. We don't have rate splitting, and in this case we have the rate splitting and common message decoding scheme, which is the proposed one. Parameters in this simulation set is 14 users, 4 base stations, 2 UAVs, and 2 antennas each. So here we can see the average rate in megabits per second over the frontal capacity in megabits per second for all of those different schemes. Figure 3 particularly, this figure particularly shows how the proposed RSCMD scheme outperforms the treating interferences noise scheme, actually for all values of the frontal capacity. And what this figure also shows is that the rates naturally increase as the frontal capacity increases due to higher throughput possibilities on the frontal links. However, on the right-hand side, we can observe a saturation of the average rates for all schemes. This is especially due to the increased levels of interference, which originates from the central cloud at high frontal capacities. What we can see is that this saturation is much more distinctive for the treating interference as noise schemes because they have inferior interference mitigation capabilities as compared to the blue curves, the RSCMD. What we further see is we can compare actually the schemes without mobile edge computing. So we can compare our proposed scheme to the CC-only scheme. It's obvious that the joint central cloud and edge cloud setup yields enhanced rates. However, at the higher values of the frontal capacity, the CC-only RSCMD performs very close to both RSCMD schemes, and this is reasonable in the view of the strong impact of the central cloud at actually the high frontal capacities. Okay, next figure. We have the achievable rate in megabits per second on the frontal capacity, and this figure particularly shows that so this figure is actually showing the proposed distributed protocol RSCMD. We have the average rates split into common and private part, and also CC and edge cloud. And for comparison, we have the TIN scheme, which does not do the splitting into private and common messages, so there will be only rates per CC and per EC. Now, this figure shows that both private and common rates increase jointly with the frontal capacity. And what is also seen is that RSCMD outperforms the treating interference as noise, especially here in the high frontal regime. And when we look at the breakdown into the private and common rate split, is that we observe that the common rate is particularly useful for the edge user. More specifically, as compared to the central cloud users, the common rates are much higher in comparatively. For example, if we check out the 100 megabits per second frontal capacity, we see that the edge cloud's common rate, so edge cloud's common rate here, achieves similar values to its private counterpart, so the edge cloud's private rate. So that shows actually that the interference management at the edge cloud seems to be a very central aspect of the proposed scheme and its effectiveness, especially here at the high frontal regime. Yeah, takeaways. We have improvements over the CC-only case and the treating interference as noise, and it seems especially effective to do the common message decoding at the edge. Now, we want to check the dynamics of the delay constraint. Parameters are 3 UAVs, 14 users, 3 base stations, and 2 antennas each. And we see here the average delay in milliseconds over the sum computation capacity in megaseconds per second. Now this curve is decreasing. That means towards the right-hand side, we have less computation capacity available. And what we see in the figure is the total delay constraint. So this is the overall allowed delay per user. And as reference schemes, we have the RCMD and the treating differences noise and their respective delays split into the transmission, the front haul, and the computation delay. Now what we see towards the right-hand side is the computation capacity is decreasing. So both edge cloud and central cloud have less and less computation capacity available. And this is also reflected in the computation delay, as we can see here. This is the computation delay of the treating differences noise scheme, and this is the computation delay of the rate splitting scheme in red. And what we can see is that up to this point, treating interferences noise is rising in its average delay. And what happened toward the right-hand side is that treating interferences noise becomes infeasible. That means it cannot produce solutions anymore that satisfy this delay constraint, which is also illustrated by this dashed line, is that the average delay in this point is almost the same as the maximum allowable one, and toward the right-hand side, so it's infeasible. And in comparison, the rate splitting common message decoding has much lower delays in comparison to the TIN scheme, and is able to cope with the much less conditions of the decreased computation capacity. So what we can take away from here is that RCMD is especially much more feasible than TIN, especially in the harsh conditions. And there's a strong trade-off capability, for example, when communication and computation resources are dynamically adjusted. What can be seen in the dynamics of here. Now, next observation, we want to check under and overloaded deployment cases. And in this figure, we show the average rate in megabits per second versus the number of users. And especially for this scenario, the number of users 16 is the break-even point between the left-hand side, which would become underloaded systems. So we have more available antennas than we have users to serve. And the right-hand side is the overloaded deployment case, where we have much more users than we have antennas to serve. And what we can see is that with increasing the number of users, the average rate per user is decreasing for both the RCMD and the TIN case in centralized and distributed protocol. What's especially interesting is that toward the right-hand side, so networks become denser. That means we have much more users within the networks. That rate splitting significantly outperforms treating interferences noise, whereas in the beginning they are almost similar. Also, an interesting point is that the distributed protocol has almost a constant gap towards the centralized protocol, even though it is much less complex and a much more practical scheme. So in general, we can say RCMD outperforms TIN, and we have the most gains in overloaded deployments. Now, let's talk about challenges and limitations of the rate splitting approach. So the rate splitting and common message decoded A-bit hybrid cloud mobile edge computing networks, we have enhanced difference mitigation capabilities within the cells and also at the cell edges at the edge clouds. And what we can do here is that we have a strong distributed and joint communication and computation resource allocation. In this case, we were able to optimize the sum rate. However, sum rate is a factor which does not consider a fair resource allocation. Talking about the resilience of these is that we have virtualized and flexible network functions, as we have had before. We do not have a single point of failure, especially as we have the multi-tier architecture. We have UAVs, we have a central cloud, which could fail, but then the others could take over. And we have the flexible access. scheme. And especially what rate splitting does now is that we are much more robust to interference cases and also can perform well under different deployment cases, for example, under an overloaded network. What we cannot tackle with this is that some users might be blocked, have blockages, or adverse channel conditions, which can hardly be tackled by using such a rate splitting scheme only. To further motivate the next section is that we can switch to a different objective which considers fairness, and that we can consider device cooperation within the network.